Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. I'm welcoming you one and all to this platform. Now, Unacademy is going to providing the GATE and engineering service classes. About myself, I G Venkata. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examination. At present, I am pursuing PhD from JNTU Kakinada in VLSA domain. First, we check how to get the Unacademy Learning app into our device. Here, just open Play Store in your device and type Unacademy. Type Unacademy and click on. Once you type Unacademy, then you get the Unacademy Learning app like this. You get the app like this, and click on this install button. It will install the Unacademy Learning app in your device. After that, once you open that app in your device, it will show what are the different courses available and who are the respective faculty handling the different subjects in that course. You get that information, and about that faculty you get brief introduction also. Now here I am going to introducing some of the top faculty from Unacademy. Ankit Goyal, he got All India topper in GATE examination in electrical stream twice. And Tiwari sir, he is a IIT topper. And Sachin Jain sir, he is the computer faculty having more than 8 years experience. And Jaspal Singh sir, he is the ex-IAS officer. Okay. Now, here are some other educators, top educators from Unacademy. Now, I am happy to announce that we are going to starting a new batches for GATE 2022 and GATE 2023. There is a Ascend batch for GATE 2023. This is for mechanical stream. Okay, here are the top educators handling the classes for mechanical students, and this batch is going to start from 8th February 2021. Okay. So next, there is a Eval batch for GATE 2022. Same for electrical engineering, mechanical engineering. Here are the top faculty handling the classes for this, and this batch also going to start from 8th February 2021. Don't forget to use my code VRAW10 during subscription to get 10% of discount. Next, there is a Ascend batch for GATE 2023. This is for civil engineering students. This batch also going to start from 8th February. Okay, here are the top faculty who are handling the classes for civil engineering subjects. And there is a Eval batch for civil engineering again. This is for GATE 2022. Okay, here are the top faculty who are handling the GATE classes for civil engineering students. For civil engineering students, this batch also going to start from 8th February. Next, again there is a Eval batch for GATE 2022. This time this is for computer science and information technology. Here are the top faculty from Unacademy for computer science subjects, and this batch also going to start from 8th February. Next, there is a Ascend batch for GATE 2023. There is a Ascend batch for GATE 2023. This is for electrical stream. This batch started from 1st February 2021. Okay, here are the top educators, and don't forget to use my code during subscription VRAW10. Okay, don't forget. to use my code VROW10. Okay, don't forget, use this code to get 10% discount. Next, again there is a SN batch. This time this is for GATE 2023 and Electronics and Communication Engineering Department. This is for, and this batch is started from 1st February 2021. So next, there is a eval batch for GATE 2022 electrical stream. Here are the top faculty who are handling the subjects. Now this batch is started from 1st February 2021, and again there is a eval batch for GATE 2022. Okay, it is Electronics and Communication Engineering Department. This batch is already started from 1st February 2021. Don't forget to use my code during subscription VROW10. VROW10. Okay. Now, there is a chemical engineering department also available here. You must thank to Unacademy to provide training for GATE examination, especially for chemical engineering students, because outside it is not possible to get the chemical engineering students, chemical engineering subjects. Okay, training. Now this is eval batch for GATE 2022 chemical engineering. Here are the top faculty who are handling the subjects, and this batch is started from 25th of January 2021. Now just we check what are the different streams available in Unacademy for GATE and engineering service examinations. Mechanical engineering, electrical engineering, civil engineering, production and industrial engineering, instrumentation engineering, chemical engineering, computer science and IT departments, and now last but not least, electronics and communication engineering. Okay, so my dear students, don't waste your time. Your learning process cannot be stopped. Whatever thing is happening at outside. Okay, join these courses in Unacademy. Be at your secure place at your home itself and get the training for GATE examination and service examinations. Okay, now if you check, now we check what are the different subscriptions available in Unacademy. See this is the plus subscription, this is the basic subscription, basic plan what we have, and next one is the iconic subscription. It is the next level of the subscription, next level of the subscription. Okay, here GATE and engineering service for preparation, you are going to assign one coach to you. One coach is assigned to you, especially for each and every student there is a special coach. Now the common points in both the cases, your classes are taken care by the India's best educators. They will teach the subjects, and interactive live classes, and structured courses and PDFs. Structured courses and PDFs. Next, live tests and quizzes. Okay, now here after completion of the test examination, see, to get a success in competitive exam, there should be proper plan, and you have to write more number of exams. After completion of each exam, okay, you have to analyze the paper, and whatever the answers you answer to that, you have to analyze, and where you commit the mistake, you have to take a note of that mistake, and in next examination not to commit such type of mistakes. So such type of plan you need, and at the same time, irrespective of continuously repeating the one or two subjects continuously, okay, after writing some exam, multiple number of exams, okay, you can assess yourself where you are strong, where you need a preparation, more preparation. Okay, that analysis you need. But students are not having that much time because they are busy with always continue preparation. Okay, and some of the students are for third year and final year students are busy with their semester examinations, classes at college, labs, all this. For that, in Iconic, once you joined in Iconic, we will take care of that thing completely. Whoever the personal coach we are assigned to you, he is going to take care of those things. Okay, it is going to be he is going to analyze the personal test analysis, and after that, based on that, they will prepare a study planner to you, and whatever the proper material, study material, they will provide to you. Proper study material they will provide. By following the study planner and by preparing the study material, definitely 200% you get the success in your competitive exams. Okay, so don't forget to join in any one of the batch, but give first priority to join in Iconic batch. Okay, here individual care is going to be a more important point here. Okay, if you observe the outside institutions, if you join somewhere to for GATE coaching, there it is a very difficult to interact with the faculty, class faculty who is coming to take the classes. Hardly you may interact 5 minutes during lunch break. Okay, personally it is not possible to interact. During class we are going to ask some doubts. Okay, but some of the students are feel shy to ask the doubt, to express their doubts in classroom. Okay, for them this is the good platform. Here only one eye to eye contact. So in online, yourself and your coach. Okay, you have to express your problem to your coach, and he will note down it, and he will assign a right person and right faculty to you to provide a solution for that problem. Okay, that is the personal coach. And if you observe the amount for this compared to outside payment what you are paying, this is not that much. See, here are the different subscriptions for plus plan: 1 month subscription, 3 month subscription, 6 month subscriptions, 12 month subscriptions. Okay, 18 months and 24 months. Now for 12 month subscription, 1 year subscription, it is a 30,250 rupees. After using my code VRAW10 during subscription, you get 10% discount. You get 10% discount. Okay, so after discount, this amount is going to be 27,225. 27,225 rupees. Okay, so that is the discount you get. This is for 1 year subscription. And if you compare this amount with the travel expenditures per a year in 12 months, so to take coaching you have to join somewhere at the time. For traveling expenditures, if you count total traveling expenditure in throughout that year, it is close to this amount. Only traveling expenditure. Okay, this is the basic plan, that's why it is this much less. Only traveling expenditure is close to this amount. Okay, and next, Iconic plan. Here we are going to provide a personal coach to you. He will take care of every aspect of your academics, every aspect of your preparation, your examinations. Okay, your materials, everything. Now for 12, here only 12 two subscriptions are available. One is a 12-month subscription, 1 year subscription, that is. Next one is a 2 years, that is a 24-month subscription. For 12 months subscription, you need to pay 45,000. After getting discount by using my code VRAW10 during subscription, you can pay 45,225 rupees. 45,225 rupees you have to pay. Okay, and for 24-month subscription, it is 70,000. After discount, it is 66,600. For third year students, this is suggestible, and for second year students, this is suggestible. Okay, here you get the personal coach. See, whatever thing is happened at outside, your learning process cannot be stopped by joining in this group. Okay, continue your learning process. Okay, Thank you. Now we are going to our topic. Last class we started the semiconductors and we discussed what is electronic devices and circuits, what is electronics, what is electronic device, what is electronic circuit, and what is semiconductor, classification of semiconductors. Okay, in that classification we discussed the direct and indirect semiconductors. First elemental and compound semiconductors, next direct and indirect semiconductors, after that intrinsic and extrinsic semiconductors. So last class we complete up to n-type and p-type semiconductors. Okay, now I am moving to the next topic. So last class we complete the mass action law. Mass action law is in a semiconductor at constant temperature, the product of concentration of electrons into concentration of holes is equals to square of the intrinsic carrier concentration. So we applied that one to n-type and p-type semiconductor, and after that we done a problem on this. Here doping carrier concentration in a semiconductor is varying with respect to distance and temperature. So at constant temperature they applied this problem, with respect to distance it is changing. So now the electron concentration is related by n of x1 equals to 5 times n of x2. Now what is the hole concentration relation, or how hole concentrations are related? So here x1 and x2 is the distance. Just I taken a semiconductor. Okay, here this is the point x1. At this point electron concentration n of x1, hole concentration p of x1, and at this point electron concentration n of x2 and hole concentration is p of x2. Now by Ohm's law, by mass action law, n into p equal to ni square. So n of x1 into p of x1 equals to ni square, and similarly at this end n of x2 into p of x2 is equal to ni square. Just I equated both. So after that I substituted this. Finally we got p of x1 equals to 1 by 5 times n of x2. This is the whole concentrations related like this. Okay, now next I am moving to Fermi Dirac distribution function. Fermi Dirac distribution function. Okay, what is this Fermi Dirac distribution function? See, by using this function we can measure the position, momentum and energy of a charged particle. Okay, by using this, here I am going to measuring the energy. Okay, and this function is represented by this equation. F of e is 1 by 1 plus e power e minus ef by kt. Here k is a Boltzmann constant. Okay, ef is the Fermi energy level. F of e is the probability function. It means probability that an energy level E occupied by an electron. That is the probability function f of e. Okay, now let us concentrate more on this equation. So this is our equation f of e, which is 1 by 1 plus e power e minus ef by kt. K is Boltzmann constant. Okay, E is energy, Ef is Fermi energy level, f of e is the probability function. Probability function. What it means? First of all, it is a probability function, means its value is in between. F of e value is less than or equals to 1 and greater than or equals to 0. That is the value of probability function, in between 0 to 1. Okay, it is in between 0 to 1. Now here, So for this, f of e, I need a clear information about f of e. So you mentioned simply it is a probability function and a probability that an energy level E occupied by an electron. What it means? See, for example, here I am going to taking 10 electrons. 10 electrons I am going to be taking here. 10 electrons. Okay, these are the 10 electrons here I am taking. Okay, now after this, these are the electron positions, different energy levels occupied by 10 electrons. Now I am defining some energy level somewhere here. This is the defined energy level. This is the energy level I defined. Now see, 4 plus 2, 6 electrons are having the energy more than this defined energy. Defined energy is E. Now 6 electrons are above the defined energy level E. Now f of E for this one is written as total possible events are 10 because total 10 electrons are there. Okay, and favorable electrons, favorable events, that means number of electrons above the defined energy level is 1 2 3 4 5 6. 6. That is the probability f of E. Okay, so my dear students, now I think so you understand what is f of E. So many electrons, so many energy levels are there. Now the things which are favorable to you, that is the probability. So favorable events by total events, that is probability function. So here in this example, in the total 10 electrons, 6 electrons having the energy level more or greater than or equals to defined energy E. So 6 by 10, that is f of E. Okay, now with respect to temperature, I am going to plotting this. I am going to plot f of E versus E, f of E versus E. I am going to plot it now. So here is a plot between E and f of E. F of E. We know one thing, maximum value of f of E is 1 because it is a probability function. Maximum value is 1. Okay. First, I am going to analyzing this at t equals to 0. At t equals to 0. T equals to 0 temperature. Once temperature T equal to 0, our equation is f of E equals to 1 by, our equation I am writing here, f of E equals to 1 by 1 plus e power E minus EF by KT. This is our expression. Okay, here now two possibilities, E minus EF. So comparing E with EF, so I am going to representing that EF value somewhere here, it is EF. Now two possibilities here, E value is less than EF or greater than EF. Let us, E value is less than EF. E value is less than EF. Once E value is less than EF, what happens? See this. E minus EF is less than 0. That means it is negative, which is a negative. Now f of E became 1 by 1 plus e power negative value by 0. So e power minus infinity. 1 by 1 plus e power minus infinity. So e power minus infinity value is 0. Therefore it is 1 by 1 plus, okay, 1 by 1 plus 0, that is 1. So for energy less than EF, probability f of E is 1. That means all energy levels are occupied. All energy levels, whatever the number of energy levels available, all those energy levels are occupied. That is the meaning of that. Now I am taking the case where f of E is greater than EF in this region. So E is greater than EF. For E is greater than EF, E minus EF is positive, greater than 0, and which is positive. So now f of E became 1 by 1 plus E power E minus EF is positive by 0. That is 1 by 1 plus E power plus infinity. Okay. E power plus infinity is infinity. So which is 1 by 1 plus infinity. So that is 1 by infinity 0. So its probability is 0 here. 0. This is the plot. The meaning of that one is at 0 Kelvin. This is at a temperature 0 Kelvin. The meaning of this one is all energy levels below Fermi energy level at 0 Kelvin are completely filled. Okay, no energy level is vacant. All energy levels are filled. That means favorable events by total events. That is 1. That means both are equal. Whatever the number of energy levels available, all energy levels are occupied. That means your defined energy level in this case is, this is the defined energy level. The defined energy level here. Now see this, above this all energy levels are filled. If your defined energy level is here, now the probability in this case is 10 by 10, that is 1. So all energy levels are occupied. Okay, that is the meaning of this. Now if you apply that one to your energy band diagram, this is similar to like this. With respect to this, less than EF all energy levels are filled, and greater than EF all energy levels are vacant. See, in a semiconductor we have, let us take this is conduction band and it is valency band. This is EV and it is EC. Just I turned the energy band diagram what we have early. I turned like this for my easy understanding purpose. At a 0 Kelvin you said in valency band all energy levels are occupied. Foreign energy levels are completely filled at 0 Kelvin. See here also all are occupied. Now you can assume, you can compare this with your valency band and you can compare this with your conduction band. Okay, and with respect to FDD, Fermi Dirac distribution, all energy levels are defined, but in energy band diagram only energy levels in valency band are defined and energy levels in conduction band are defined. So the energy gap is not defined. So with respect to FDD, when you are comparing your energy band diagram with FDD, you can treat both EC equals to EV. Okay, next. Now we take it to different temperatures. What happens? We check it. See, this is the plot for at T equals to 0. This is the plot for T equals to 0, or that. This is the plot at T equal to 0, EF. So it is 1. Okay, that is the case at T equals to 0. Now for T not equals to 0, that means some temperature, at some different temperature, and before going to different temperature, I am going to calculating the value of f of E at E is equals to EF and T not equals to 0. Okay, so for E equals to EF, our equation is basic equation is this one. This is our basic equation. F of E is 1 by 1 plus E power E minus EF by KT. This is our expression. In this, I am substituting E equals to EF. So now F of EF equals to 1 by 1 plus E power E minus EF, because E became EF. Now E minus EF equal to 0, 0 by T, T not equals to 0. So this is E power 0. Once E power 0, it is 1. 1 by 1 plus 1. So that is 1 by 2. 1 by 2 is the half of the probability, half of the value. So that is the average energy level, average value. So at E is equals to EF, probability of occupancy is half, 1 by 2, average. So at a 0 Kelvin, maximum energy level occupied by an electron is Fermi energy level. And for E temperature greater than 0, the maximum energy level is greater than Fermi energy level. Okay. Now, we apply this plot for T greater than 0. See, here we observed once temperature is increasing, this is your valency band and it is a conduction band. So first covalent bonds which are close to this are going to break, and electron will move from here to conduction band and occupy the energy level immediately, which is after EC. Okay, if more temperature, covalent bonds here, these covalent bonds are breaking and they occupy the energy level somewhere here, like that. Okay, the same thing I am going to be applying here. So this is the plot. So it is a F of E, and on x-axis we are taking E, energy. Now comparing with EF, somewhere here is EF at 0 Kelvin. This is the plot what we get, EF. Now this is EC EV. You can compare, this is nothing but our EC equals to EV. Now this is treated as a valency band, this is treated as conduction band. Once temperature is increasing, what happens? See this, once temperature is increasing, first the covalent bonds which are just below the Fermi energy level or valence, just below the EV, are going to break. Okay, once these covalent bonds are breaking, here probability of occupancy is less, vacancy is more, because they are breaking. Now the electrons which are moving from valency band to conduction band are immediately occupy the energy levels which are defined immediately after EC. So they are occupied here. Now probability of occupancy after EF is going to be increasing. That means after EC is going to be more. So that's why. And one more thing, this is 1, this is 0, this is 1 by 2. At E is equals to EF, temperature not equals to 0, the maximum probability is 1 by 2. That's why it is 1 by 2. Okay. Now at less than EF, that means less than this EV, vacancy is there, occupancy is less, occupancy is decreasing because covalent bonds are breaking. But at far end of this, at this point, there is no breaking of covalent bond. So all energy levels here are occupied by moving towards the Fermi energy level. That means by moving towards valency band, breaking of covalent bonds is there. Now probability of occupancy is going to be decreasing. But at anyway, at E equals to EF, it became 1 by 2. Now we are moving to EC, conduction band. Now in conduction band, here probability of occupancy is more. By moving away from towards the conduction band upward, your probability of occupancy is decreasing. So occupancy is decreasing. This is for temperature T1. T1 is greater than 0 Kelvin. Okay. So this is the FDD, Fermi Dirac distribution. Now by applying this FDD, we are going to calculate the average energy level of an electron. See, practically it is not possible to identify the energy level of a particular electron in a semiconductor, but it is possible to identify the average energy level of that semiconductor. Average energy level is possible. Okay, now we go on calculate that average energy level. Okay, Now by applying that FDD to our semiconductors, we can identify that. Now I am going to apply Fermi Dirac distribution to semiconductors. Before going to this, I want to clarify something. See that this is the energy band diagram, a plot between this energy band diagram, EC, and it is EV. On this axis, I am taking probability function f of E. The minimum value is 0, maximum value is 1, and here is 1 by 2. It means at E is at this point f of E equal to 1 by 2, at E is equals to EF, and this is EC, because it is a conduction band, and it is valency band, it is EV. Fine. Now, so f of E, now if you with respect to this, you can write it as f of EV. With respect to this, you can write f of EC. Here f of EC is represented as, we called it as probability of occupancy in conduction band. Probability of occupancy in conduction band. See, because in conduction band we have plenty of electrons. Those electrons are going to occupy some energy level. So that's why we called it probability of occupancy. And f of V is called also a probability of occupancy, but in valency band. Probability of occupancy in valency band. Probability of occupancy in valency band. Okay, now here but in valency band we are going to representing a hole. So to represent that hole, we need to use a probability of vacancy, that is 1 minus f of EV. That is probability of vacancy, because occupancy plus vacancy is 1, because total probability is 1. So now it is probability of vacancy. Probability of vacancy in valency band. And one more thing, when you are dealing with conduction band, you are going to using this. When you are dealing with valency band, you have to be use this, because in conduction band we have free electrons, and in valency band we have holes. Okay, so now onwards we are going to dealing with the f of EC and 1 minus f of EV. For n-type semiconductor, more number of electrons we have, more number of electrons, that means f of EC is greater than 1 minus f of EV. Okay, and in p-type semiconductor, holes are more majority charge carriers and electrons are minority. It means 1 minus f of EV is greater than f of EC. Next one is intrinsic semiconductor. In intrinsic semiconductor, electron concentration equals to hole concentration, so both are equal. So f of EC and f of EV both are taking in this direction. This is a f of E, and in this direction you can take 1 minus f of E, because maximum value of f of E is 1. In this direction you can take 1 minus f of E. So it is 1 minus f of EC, 1 minus f of EV, f of EC, f of EV. Okay, so this is the basic thing you need to be understand to apply the FDD to semiconductors. Okay, now I am going to applying this FDD to my semiconductors. So total three type of semiconductors we have: intrinsic, N type and P type semiconductor. First I am going to drawing that semiconductors energy band diagram. That is for intrinsic, and this is for N type. And next for P type. For P type. So EC, EV, okay, and this is F of E. F of E. So F of E values are, this is 0, it is 1, it is 1 by 2. It is 0, 1, 1 by 2. 0, 1, 1 by 2. So it is EC, EV, EC, EV, EC, EV. Simultaneously, I am going to analyzing all parameters, all type of semiconductors. It is intrinsic, semiconductor, and this is a N type, and this is P type. Let us. We know one thing, in intrinsic semiconductor, electron concentration equals to hole concentration. That means N equals to P equals to Ni. We know that. In probabilities point of view, for intrinsic semiconductor, probability of occupancy in conduction band F of EC equals to probability of vacancy in valency band 1 minus F of EV. That is the point. Okay, now from this side F of EC, let us take this is F of EC, and 1 minus F of EV is this much. From this side, this is F of EV. Both are equal. Now I am going to plotting an imaginary line to combine this. Now just extend this 1 by 2. Why? Because at E is equals to EF, at E is equals to EF, that means Fermi energy level probability of occupancy is 1 by 2. This is EF. This is intrinsic, that's why subscript I added. EFI is the intrinsic Fermi energy level. EFI is the intrinsic Fermi energy level. Okay, because at 50, all these cases are T not equals to 0 conditions, sir. At T not equals to 0, E is equals to EF, F of E equals to 1 by 2. That is the point I used here to get the Fermi energy level. So intrinsic Fermi energy level is approximately midpoint of this energy gap. Okay, approximately midpoint of that energy gap. Okay, next one is N type. In N type, we know that electron concentration is more than hole concentration. Electrons are majority charge carriers. Now here we can write probability of occupancy F of EC is greater than probability of vacancy 1 minus F of EV. Okay, so from this side I am taking probability of occupancy. This is probability of occupancy. and probability of vacancy is small in this, small in this. Okay, now just join this an imaginary line like this. Now just extending this one. Now this is the intersecting point. It means this is the Fermi energy level of n-type semiconductor. EFN, Fermi energy level of n-type semiconductor. Use like this, EFN and EFI. EFI and EFN, Fermi energy level of n-type semiconductor. Similarly, I am moving to p-type semiconductor. In p-type semiconductor, you observed or not, holes are majority charge carriers. Holes are greater than n. That means probability of vacancy in valency band is more compared to probability of occupancy in conduction band. That means EF of EC is less than 1 minus F of EV. So this is 1 minus F of EV. This is F of EC. Now I am writing an imaginary line to join these 2 points like this. Now just extending this point here. This is the intersecting point. It means this is the Fermi energy level of this semiconductor, p-type semiconductor. Okay, so that is EFP. EFP, Fermi energy level of p-type semiconductor. Okay, and in some textbooks they mentioned this one by EP. Okay, and some textbooks and it was mentioned by EN, and F of EFI is mentioned as EI. They mentioned it as EI. Okay, don't get confused. Okay, don't confuse sir. Now this is the, so far we applied FDD to semiconductors. From this you observed one thing. In intrinsic semiconductor, Fermi energy level is approximately at midpoint of the energy gap. By applying one condition, effective masses of electrons and holes are equal. At that time only it is midpoint. Later we verify that. And at the same time in n-type, by adding impurity of Nd, electron concentration is increasing. Electron concentration is increasing. Okay, so once electron concentration is increasing, average energy of electrons also increasing. That's why Fermi energy level is moving upwards. Okay, here by doing Nd, Na doping, by doing, electron concentration is decreasing because electrons are minority charge carriers in p-type. We know that by increasing amount of doping in a semiconductor, majority carrier concentration increases but minority carrier concentration decreases. So whole electron concentration is decreasing by increasing Na value, by adding Na. So that's why average energy is also going to be decreased. This is EFP. If you are doing more doping, this energy level is going to be moving close to this, and more doping of Na close to this. If heavy doping, then this Fermi energy level is entered into this. Such type of semiconductors are called as degenerative semiconductors. We discussed in detail about this degenerative semiconductors in tunnel diode. Tunnel diode is the device which is designed by using heavily doped p-type and n-type semiconductors. Okay, such type of semiconductors, heavily doped semiconductors, are called degenerative semiconductors, and mass action law is not applicable to that semiconductors. Okay, yeah. Now see, here are the some important points you need to be considered. Already we discussed these points. See, in an intrinsic semiconductor, EF is the approximately at midpoint of energy gap. In n-type semiconductor, Fermi energy level is close to EC. In p-type semiconductor, EF is close to EV. In n-type semiconductor, by increasing doping, EF is moving towards conduction band, and if doping is very high, EF enters into conduction band. So this type of semiconductors, we call it as a degenerative semiconductors, we call it. Okay, next one is, in p-type semiconductor, by increasing doping, EF is moving towards valency band, and for very high doping, it enters into valency band. Okay, now very high doped semiconductors are called degenerative semiconductors. Mass action law is not applicable to that. These are the important points you need to be considered, okay, with respect to Fermi energy level. Now see, let us, I am going to a small mathematical part. Let us, I am taking first intrinsic semiconductor with the Ni equals to okay, I am taking only Ni value 100, just to take Ni equals to 100 per centimeter cube. So here Ni is 100. Ni 100 in this sense, number of electrons equals to 100 as well as number of holes also 100 in that. Okay, now it is doped with Nd of 900. 900 impurity atoms I added to that. Let us, I added 900 phosphorus atoms to this. These 900 phosphorus atoms provide 900 positive immobile ions plus 900 electrons. So here you are taking 900, now here are 900 and here is 900. Anyway, by adding this impurity, 900 electrons are added to your semiconductor. So Nd is 900, so 900 electrons are added to this. Now there is no hole. By adding the Nd, you are not going to adding any excess hole to that. Now after that it became a 1000 and it became 100. From this, what we conclude, by doping, majority carrier concentration is increasing and minority carrier concentration is no change. So far up to this point, no change, but on paper it is. But actually within the device, what happens? Once you are adding excess external impurity to that, additionally, already in this semiconductor intrinsic condition, 100 electrons and 100 holes are available. You are saying these are the whole electrons available. Let us these are the holes available, they are equal in number. Once you are trying to add this impurity to this, in this sense, externally you are adding 900 electrons to this. Externally you are adding 900 electrons to this. By adding 900 electrons to this, what happens? In this 900, few of the electrons are going to recombine with the holes. That means they are forming covalent bond. So this covalent bonded pair you have to be neglect. That's what I am doing in the next case. See, sorry, it is I am taking 100. Okay, sorry, electron concentration is 1000. After that, 1000 electrons, 100 holes. Now a recombination I am taking 30. Now it is minus 30 and minus 30, so 970 and 70. From this, what we observed, majority carrier concentration is increasing because initially electrons are only 100 in a semiconductor. After adding a 900 impurity atoms to that, it is increased from 100 to 970. So there is an increment in majority carrier concentration. And at intrinsic condition, number of holes are 100. Okay, 100. But after increasing the amount of doping, that means after adding doping to that, it is changed from 100 to 70. That means 100 to 70 means minority carrier concentration is decreasing, and here we observed majority carrier concentration is increasing. Okay, if I add somewhat more impurity, let us I added 200 more to this, plus 200 to this. Now it will add plus 200 to this. Okay, no hole initially. Okay, and after that you need to remove the recombination. Now minus 10 additional recombination, minus 10. Okay, now it is 190 has to be added to this. Now plus 190 and minus 10 recombination. So this is 60 and 0 6 11 1160. So by increasing amount of doping, majority carrier concentration is increasing and minority carrier concentration is decreasing. It is first from 100 to 70. Now it is 100 to 6, 70 to 60. Like that. In any semiconductor, by increasing amount of doping, the majority carrier concentration is increasing and minority carrier concentration is decreasing. Okay, so that is the very important point in theoretical point of view, as well as to analyze our PN junction diode in detail. Next, now I want whatever the semiconductor I have, it may be intrinsic, N type or P type. Is it electrically negative, positive or neutral? Okay, see, first, once you take one semiconductor and if you want to say that is electrically neutral, means okay, net to positive charge equals to net to negative charge. In that case only you can claim that is electrically neutral. Okay, if more amount of negative charge, then you can call it as negatively charged, and if it is more positive charge present in that, then you can claim it as positively charged. Now in this case, what are the what is the net negative charge and what is the net positive charge, and what is the electrical point of view, how it behaves? Is it neutral, negative or positive? See, so total negative charge is number of electrons are 970, fine. Now number of holes is 70, these are the positive, and not only these holes, previously by adding 900 phosphorus atoms to that, by giving 900 electrons to you, those phosphorus atoms became positively charged, positive ions. So 900 positive phosphorus atoms are positive phosphorus ions are available. Now I am going to adding that. So positive ions are 900 available to you. So these are 900. These are positive. These are positive. So total net to positive is 970 and total negative is 970. Both are equal. Okay, so once the net negative charge equals to net positive charge, then we said that semiconductor is electrically neutral. Semiconductor is electrically neutral. Now, similar way, your p-type semiconductor also electrically neutral. In intrinsic semiconductor, we know that electron concentration equal to hole concentration equal to Ni. So, it is also electrically neutral. So, any semiconductor at any instant you can take, it is electrically neutral. Okay, that is very important point. Okay, so by a semiconductor is electrically neutral. Now here, so far we discuss only theoretical part. Once you take a semiconductor, what are the majority charge carriers and what are the minority charge carriers, and how that carrier concentration is changing or varying with respect to amount of doping. We know that. Okay, we know that. Now, and energy band diagram also we studied. Now what I am going to doing is, I want whatever the things so far I discussed, everything in a proper equation point of view. So quantitative analysis. So far we done qualitative analysis. There is no quantity. We did not specify this is this much. This is this much. We did not specify like that. But now I am going to specifying that this is this much. This is something. This is something. This is the quantity this much. Like that. So now we are moving to quantitative analysis. Quantitative analysis. Okay, so now I am moving to that quantitative analysis. Clear? So for that, see, you need to consider two important points. Two important points you need to be considered. See, in any semiconductor you can take any semiconductor. It may be a intrinsic semiconductor, extrinsic semiconductor, whatever it is. Electron concentration is represented by an equation called Nc into e power minus of Ec minus Ef by kT. Nc into e power minus of Ec minus Ef by kT. So K is Boltzmann constant. We know that Ec is the minimum energy level of conduction band, Ef is the maximum energy level, Fermi energy level, and T absolute temperature. Nc is density of states in conduction band. Now, the value of Nc is 2 into 2 pi into Mn star into kT by h square whole power 3 by 2. That is the Nc value. Okay. Here Nc is density of states in conduction band. What it means? See this. See this. Here, this is valency band. Now from this point onwards, it is conduction band. Ec. This is conduction band. Okay. Band in this sense, multiple number of energy levels are placed in that. Multiple electrons are available in that band of energies. Now that energy levels are defined how much density or how much close they are. See this, here energy levels are this much close, this much close. How densely these energy levels are, that is the Nc value. Okay, see, in some cases that energy levels are going to be like this also. See, for example, if you consider in this case, the density of energy levels in this case is less, not that much density, but here more density, that is the Nc value. Similarly, the whole concentration we can define it as P equals to Nv into e power minus of Ef minus Ev by kT. Ev, we know that maximum energy level of the valency band, and Nv is the now density of states in valency band, because in valency band we have already occupied energies, that means covalent bonds. Okay, that is the valency band. Clear? Now Nv is the density of states in valency band. Now here one more point you need to observe. Nc is value is 2 into 2 pi into Mn star kT by h square whole power 3 by 2. K, Boltzmann constant, we know that. Absolute temperature 2 pi constant, h is a Planck's constant, and Mn star is the effective mass of the electron. So whatever the mass of the electron, you know already, 9.1 into 10 power minus 31 kg, we called it as mass of a free space particle, 9.1 into 10 power minus 31 kg. Okay, that is the mass of a free space particle. Free space in this sense, under vacuum conditions they calculated the mass of the electron here. Okay, but once you take your semiconductor, and in your semiconductor your electron is subjected to different type of forces on that. From adjacent electrons it is going to be repulsive force, from negative immobile ions again a repulsive, from positive immobile ions there is attractive force. Now in a semiconductor your electron is subjected to different type of forces. Under all these forces, the mass of the electron under all these conditions is represented as effective mass of the electron. Okay, so that is represented in terms of m naught. Okay, similarly for nv we can write it as nv is 2 into 2 pi into mp star kt by h square whole power 3 by 2. These are the values of nc and nv. Now by substituting the values of kt, we know that we don't know the T temperature value. K value we know, H square value we know, except Mn star and T, you know the remaining things. By substituting the values and simplifying, you get the value of Nc this much, 4.8 into 10 power 21. Now Mn star by M naught whole power 3 by 2 into T power 3 by 2 per meter cube, or per, same thing here also, instead of Mn star you get Mp star. This is in meter cube. Okay, now if you want you can take per centimeter cube also by converting that meters into centimeters. Okay, now Boltzmann constant 1.38 into 10 power minus 23 joule per Kelvin. So these are the values of Nc and Nv. So during problems you can substitute these values directly. 90% they will give the value of this. They given it's okay, otherwise you can use this one. Now next, now I am going to an important topic, that is charge neutrality. Just before we studied this we know what is charge neutrality. The net negative charge equals to net positive charge. Then we said it is electrically neutral. And just before we concluded, semiconductor is electrically neutral. A semiconductor is electrically neutral. Okay, now see this here. First I am taking an intrinsic semiconductor. Here I am going to take, and here I am going to be doing a compensate doping. Compensate doping in this sense, both Na and Nd are added to that. Both Na and Nd both are added to that. Both the type of impurities are added to that. That is the compensated doping. Now here already in this semiconductor electrons are available and holes also available to you before adding amount of doping. And after that I am going to adding impurity to this. After adding impurity to this, by adding Na, okay, it provides negative immobile ion to us and it provide holes to you. Already we represented a hole. All the holes I am representing by a single one here for easy understanding purpose. Similarly, by adding Nd to this, it became a positive immobile ion and it provides one electron to you. Each atom provides single electron to you. Now here, so this electron already represented by this total number of electrons, this much negative. Now manually, this is Na number of negative immobile ions. Here we have finally negative atom immobile ions are Na, positive immobile ions are Nd, and electron concentration is, number of electrons are N, electron concentration, hole concentration is P. So negative immobile ion concentration is Nd, negative electron concentration is N, positive immobile ion concentration is Nd, hole concentration is P. Okay, now once it is electrically neutral, the net negative charge is equal to net positive charge. This is the net negative charge, Na plus N equals to net positive charge, this one plus this one, whole concentration P plus amount of Nd what you added. This is the charge neutrality condition. So your semiconductor should satisfy this condition. Na plus N equals to P plus Nd. Okay, and we know that N is the electron concentration and P is the hole concentration. Okay, now here I am going to analyzing the topic at two different conditions. First condition is by knowing the type of semiconductor. Second condition by knowing the type or amount of doping. In this case, I know the given semiconductor is intrinsic N-type or P-type, but I don't know the amount of doping. But next case, I don't know the type of semiconductor, just I know the type of doping what you added, Na or Nd you added, or how much Na and Nd you added. Only that information I know. Okay, from that information, from the knowledge of this, you need to calculate electron and hole concentrations in a semiconductor. Now first I am going to moving to first case. See this? By knowing the type of semiconductor, I know the type of semiconductor. Anyway, this is our standard equation. Na plus N equals to P plus Nd. Okay. Now Na plus N equals to P plus Nd. Let us, I am taking first N-type semiconductor. Okay. Sorry, before going to that, I am taking intrinsic semiconductor. For intrinsic semiconductor, we know that electron concentration equals to hole concentration equals to Ni. Just substitute this one here. Now, Na plus Ni equals to Ni plus Nd. So here, this one gets cancelled. Therefore, Na equals to Nd. So, in a semiconductor, if you add both Na and Nd are equal amount, then that semiconductor behaves like an intrinsic semiconductor. Even though you added impurity, no use of that. Okay, that is the intrinsic. Just you added amount of Na and amount of Nd, both are equal values. Okay, both are equal values. Next one is I am going to taking N-type semiconductor. N-type semiconductor I am taking. Okay. So in N-type semiconductor, we know that. So you concluded that it is a N-type semiconductor. Once it is N-type semiconductor, amount of doping except or impurity concentration is 0. You are not adding any Nd. No Nd is present in that. Sorry, no Na is present in that. Because it is N-type. Clearly you are saying N-type. To get N-type, just you are going to adding Nd. Okay. So Na equal to 0. That is the first point. So Na equals to 0. Now, electron concentration I am taking it as Nn and hole concentration is Pn. Or if you want, you can take it N0 also under steady state condition or under thermal equilibrium condition. And hole concentration is P0. You can represent like this also, no issue. Okay, now we have mass action law. Now I am going to mass action law is N into P equal to Ni square. So which is nothing but Nn into Pn. From this Pn value is Ni square by Nn. Okay, now take these values so far. Nn is now Na is 0, N equals to Nn and Pn equals to Ni square by Nn. Take this value, substitute in these equations. Now our equation is Na plus N equals to nd plus p. Okay, na plus n equals to nd plus p. Here the values, na equals to 0 and n equals to nn and pn equals to ni square by nn. Just take these values, substitute here. 0 plus n equals to nn equals to nd, amount of impurity you added, pn is ni square by nn. Simplify this equation. Now, so just taking LCM and taking this nn this side. Now it is nn square minus nd into nn minus ni square equal to 0. This is the second order equation in terms of nn. Okay, so it is like ax square plus bx plus c equals to 0. It is like, now we need the value of nn, x value. Now the value of that one is, we can write minus b. So that equation value is minus b plus or minus square root of b square minus 4ac by 2a. That is the equation for this. Okay, now substitute the values in this. Therefore, similar to this, one can write nn is minus b is minus nn minus nd, this is my b value, minus nd plus or minus square root of b square means minus nd square minus 4a value, here coefficient of nn square is 1, into c value minus ni square by 2a. A is 1. By simplification, minus into minus plus, it is nd by 2 plus or minus square root of minus nd by nd square, it is nd whole square is nd square. By taking 2 into roots, it became 4. Now 4 can be written as 2 square, so nd by 2 whole square plus minus into minus plus, this 4 and this 4 gets cancelled, ni square. This is the next level of equation for nn. This is the number of electron concentration. But one thing, in general, amount of doping what we are adding is nd is much greater than ni value in general. Once it is much greater than this value, so compared to this, it is negligible. Once this ni square is negligible, once it is negligible, now nd by 2 whole square root and 2 gets cancelled, it is nd by 2 plus or minus nd by 2. nd by 2 plus nd by 2 is nd by 2 minus nd by 2 is 0. So in any semiconductor, okay, for a temperature greater than 0, that means at room temperature mostly, no chance of getting majority carrier concentration 0. No chance of getting majority charge carriers 0. That's why I am going to removing this negative symbol. Therefore, the value of nn is finally exact value of electron concentrations are I am writing nd by 2 plus square root of nd by 2 whole square plus ni square. This is the value of exact value of electron concentration in a semiconductor. Okay, and we know the whole concentration P is ni square by nn, no change in that. Just calculate nn value, substitute that nn here, then you get the pn value. Now here is our condition. After applying this condition, this is negligible. By neglecting that, nd by 2 whole square root, but will cancel. Nd by 2 plus nd by 2 is nd. Therefore, nn is approximately nd. Okay, so 99% of the cases you get this one. In a semiconductor of n type, amount of doping Nd is much greater than intrinsic carrier concentration. So much greater than means to express the external behavior, a semiconductor doping is minimum 5 times Ni. Okay, for extrinsic behavior. Okay, now see this. After this, if Nd is much greater than Ni, at that time you can write electron concentration in that semiconductor of n type is approximately amount of doping what you done, and hole concentration is Ni square by Nd. So this is the final point you should be conclude. So my dear students, please note down this point. This is very important. Okay, once they given the amount of doping and intrinsic carrier concentration to you, from that you can get the amount majority carrier concentration and minority carrier concentration. Okay, this is for n type. Next we go and take p type. Let us take, this is the analysis we done already. Next, now I am moving to a p-type semiconductor. That means the given semiconductor is a p-type. Only that portion I know. Once it is p-type, just I am going to concluding that nd equal to 0 and n equals to np, p equals to pp. And from mass action law, np equal to ni square and np into pp. So np is ni square by pp. Just before what we done. So simple, sir. Once it is p-type, amount of donor impurity is 0. Whole concentration pp is, sorry, P is whole concentration, I am taking pp, and electron concentration is np. Okay, so the subscript represents type of semiconductor. Okay, now by substituting these things in our standard equation of Na plus n equals to Na plus n equals to nd plus p, this is our standard equation. In that I am substituting the values of nd, p and n values. By substituting Na, it became Na plus n became np equals to nd 0, p became pp. So we get, by simplifying this, you get the same value similar to the previous case. See this. So here also a second order, it is a second order equation. Now I am getting pp value, exact value. So after everything, the exact value of pp is, now pp value is Na by 2 plus square root of Na by 2 whole square plus Ni square. This is the exact value of whole concentration in a semiconductor. But most of the cases, 99% of conditions, amount of doping is Na is much greater than Ni. In that case, majority whole concentration pp is approximately amount of doping Na, and whole concentration np is Ni square by Na. Ni square by Na from mass action law. So my dear students, please note down this point also. Please note down this point also. pp is Na and np is Ni square by Na. Okay, please note on that point. So far we know, in a semiconductor, once they given amount of doping, from the knowledge of that, with the help of intrinsic carrier concentration, you are in a position to calculate majority carrier concentration and minority carrier concentration. If doping is much greater than Ni, then you go for approximate model like this. So majority carrier concentration is amount of doping and minority is Ni square by amount of doping. If it is not that much, or 1.2 times or 1.3 times like that, okay, then you go for exact value. So exact value is Na by 2 plus square root of Na by 2 whole square plus Ni square. But getting exact, but rare conditions we are using exact value. 99.99% we use approximate value. This is the first case. Just by knowing the type of amount of doping, we mention the we know the type of semiconductor. Next part is by knowing type or amount of doping. Here I don't know the type of semiconductor what it is, but I know the value of Na and Nd. So compensate doping they are going to. Now let us, I am taking first case, Na equals to Nd. Let us, once Na equals to Nd, just substitute that one here. Now I am replacing this Na by Nd. Nd plus N equals to Nd plus P. This one and this one gets cancelled. Now N equals to P. So the only semiconductor which maintains N value equals to P is the intrinsic semiconductor. The only semiconductor which maintains N equals to P is intrinsic semiconductor. So now I am concluding that in a semiconductor, once the amount of doping Na equals to Nd, then that semiconductor behaves like an intrinsic semiconductor itself. Okay. Now I am going to adding some impurity variation I am trying to maintain. Let us, now this is compensate doping. I am adding Na and Nd both, but Nd is greater than Na. Nd is greater than Na. So once Nd is more, you mentioned, immediately it became N-type semiconductor. And net doping is Nd minus Na. Net doping is Nd minus Na. Okay. Now, the exact value of electron concentration in a N-type semiconductor, previously we've written Nd by 2 plus square root of Nd by 2 whole square plus Ni square. This is the equation we derived. This is the equation we derived for exact value of electron concentration in a N-type semiconductor. Previous case, only amount of doping is Nd, but in this case, amount of doping is Nd as well as Na. Now, the net doping is treated as the here main point. Now, net doping is Nd minus Na. Once net doping you know, immediately now this equation became Nd minus Na, net doping by 2 plus Nd minus Na by 2 whole square, net doping by 2 whole square plus Ni square. Only that is the modification in that. This is the exact value of majority carrier concentration. If you want minority, just simply Ni square by majority. Now, for example, in that case, let us net doping is much greater than Ni. Net doping is much greater than Ni. In that case, you can omit all this part. Simply you can take Nn is Nd minus Na. That is the majority carrier concentration. Majority carrier concentration is equals to net doping and minority is Ni square by net doping. That's it. That is N-type semiconductor. If Nd is greater than Na. Similarly, I am going to applying the same thing for P-type. That means Na is greater than Nd. So once you concluded it is Na is greater than Nd, now it is P-type semiconductor. From this data, simply I am writing it is P-type semiconductor. So already you know that how to represent a P-type semiconductor. Majority carrier concentration in a P-type semiconductor. So the value of Pn value already we derived is Na by 2 plus square root of Na by 2 whole square plus Ni square. We know that. But in this case, we are not adding single doping. We are adding two different type of materials. That is compensate doping we are doing. Now this equation became simply, in place of Na, write Na minus Nd by 2 plus Na minus Nd whole square by 2 plus Ni square. This is the value of Pp. Whole concentration in a P-type semiconductor. For example, net doping is much greater than Ni. Net doping is much greater than Ni. In that case, Pp is approximately equal to net doping Na minus Nd, and Np is Ni square by net doping. Okay. So far, whatever the two possible conditions we have, we analyzed those two possible conditions. Okay. Next one. Now, I want to calculate the Ni value. I want to calculate the Ni value. See how I am going to calculating Ni value. We know about intrinsic semiconductor. Electron concentration equals to hole concentration equals to Ni. And we know mass action law, N into P equals to Ni square. And we know one more thing, in any semiconductor, electron concentration value, hole concentration value. So electron concentration, we know that Nc into e power minus of Ec minus Ef by Kt. Let us take it as equation number 1. And next P is Nv into e power minus of Ef minus Ev by Kt. Let us take it as equation number 2. Okay, equation number 2. And you are saying this is a intrinsic semiconductor. For intrinsic, N into P equal to Ni square, and N equal to P equal to Ni just before you mentioned. Now take these values of N and P, substitute in this equation. Now N into P equal to Ni square. So Ni square is N value and P value. Whatever the values we have, whatever the values of N and P, just I am substituting the values. Yeah, that is N and this is P. Now simplify this. I am simplifying this. See this? Now by simplifying that, Nc Nv into e power minus of Ec minus Ev by Kt. Our equations are Ni square equals to Nc into e power minus of Ec minus Ef by Kt into Nv into e power minus of Ef minus Ev by Kt. Just simplify these two. Okay. Now Nc into Nv, that was I've written here, Nc into Nv into e power. So Nc into Nv into e power minus Ec, minus into minus plus Ef, so minus Ef minus into minus plus Ev by Kt. So now this Ef and this Ef gets cancelled. So this is Nc into Nv into e power minus of Ec minus Ev by Kt. And we know one thing, Ec minus Ev is nothing but energy gap. So Nc into Nv into e power minus Eg by Kt. So that is the equation for Ni. Square it is. Now take root this side, then you get the Ni. So this is Ni square. Just I substituted the values of Nc and Nv also here. After substituting the values here, this is e power minus Eg by Kt. I am taking that one as it is. Here t power 3 by 2 and t power 3 by 2, t power 3 by 2 and t power 3 by 2. So t power 3 by into t power 3 by 2 is t cube, t cube, and remaining is total constant. Remaining is total constant. This part and this part is constant. Now for my easy understanding purpose, I am representing that constant by a. And once you take this square root, this square this side, it became a square root. Now it became square root of a. Now I am taking that square root of a is simply a naught. So ni is a naught into t power 3 root. So t power 3 by 2 into e power minus eg by 2 kt. Eg is energy gap. So therefore your final Ni value is a naught into t power 3 by 2 into e power minus Eg by 2 kt. Eg by 2 kt. This is the expression. Okay. So that is the Ni value. Now based on Ni value, we have very nice problems. During problem sessions, we solve the problems. Yeah, here also problems are there. Now just I am going to introducing the mass action law. So based on that, I am going to solving problems. So 1, 2. Okay. Now total 6 problems. Now we go on solve that problems. Yeah. See this? The intrinsic carrier concentration of silicon sample at 300 Kelvin is 1.5 into 10 power 16 per meter cube. So they given Ni value 1.5 into 10 power 16 per meter cube. Next, after doping, the number of majority carriers is, so majority carriers, so the number of majority carriers is 5 into 10 power 20 per centimeter cube, sorry, per meter cube they given. Now what are the minority carrier density? So minority carriers are how many? Okay, see, already we have mass action law. So mass action law is n into p equals to ni square. Now in place of n and p, I am going to substituting the, see, if you take any type of semiconductor, if it is n type semiconductor, it became majority carrier concentration. In n type, n became majority carrier concentration. So majority carrier concentration. Majority carrier concentration, and P became minority carrier. So into minority carrier concentration. So majority carrier concentration into minority carrier concentration equals to Ni square. You can write like this also. So you can convert your mass action line to different forms. Okay, so now they given majority carrier concentration to you. They given this majority carrier concentration 5 into 10 power 20 and Ni value 1.5 into 10 power 16. So minority is how much? Is equals to Ni square by majority. Therefore minority carrier is Ni square means 1.5 into 10 power 16 into square, it is 1.5 into 10 power 16 by Ni square by majority. So majority is 5 into 10 power 20. 5 into 10 power 20. Now just simplify that. So it is 5, it is a 0.3 times, now 16, it is 20, now it is 10 power 12, 10 power 12. So 0.3 into 1.5, it is 0.45. So or 4.5 into 10 power 13 per meter cube. This is the minority carrier concentration. Check the options here. 4.5 into, sorry, it is a 12.45 you get. So by taking it is 10 power 11. Sorry. So 10 power 11 per meter cube. So here is 4.5 into 10 power 11 per meter cube. So during calculation be cautious. So like that you can calculate once the intrinsic carrier and majority carrier given. Now sometimes they give intrinsic as well as amount of doping. From that also you can calculate majority and minority carriers. See this problem. A silicon bar is doped with the donor impurities Nd equals to 1.5 into 10 power 15 atoms per centimeter cube. Given the intrinsic carrier concentration of silicon at T equals to 300 Kelvin is Ni equals to 1.5 into 10 power 10 per centimeter cube. Assuming complete impurity ionization. The meaning of complete impurity ionization is whatever the amount of impurity you added, all impurity added 1.5 into 10 power 10 per centimeter cube. Okay, you observed or not? Here, compared to Nd is 10 power 5 times more. That means 1 lakh times more. So, Nd is much greater than Ni. Then immediately you can write, because of Nd it is n-type semiconductor, therefore electron concentration is under steady state. This is n-type, or you can write it as Nn is approximately amount of doping Nd and whole concentration is N Ni square by Nd. Just simplify this. It is 1.5 into 10 power 10 per centimeter cube. And here it is 1.5 into 10 power 10 into 1.5 into 10 power 10 by Nd. 1.5 in, sorry, it is 10 power 15, sir. Sorry. So 1.5 into 10 power 15. Now just simplify this. So 1.5 gets cancelled. Now it is a 10 power 5 gets cancelled. Therefore, whole concentration is 1.5 into 10 power 5 per centimeter cube. That is the value of whole concentration. So it is 1.5 into 10 power 15 electron concentration and whole concentration is 1.5 into 10 power 5. So option is A. So that is your answer. Now I am moving to next problem. See, consider a silicon sample doped with Nd 1 into 10 power 15 per centimeter cube donor atoms. So they given Nd value 1 into 10 power 15 per centimeter cube. Assume that the intrinsic carrier concentration Ni, they given Ni 1.5 into 10 power 10 per centimeter cube. If the sample is additionally doped with Na, so whatever the sample you have initially doped with Nd, now it is additionally doped with Na. So Na value they given 1 into 10 power 18 per centimeter cube. Okay, now, so this is comes under compensate doping. They want approximate number of electrons per centimeter cube. Here we observed Na is greater than Nd, that to 1000 times greater compared to this, 1000 times more. So now the net doping I am writing it as Na minus Nd. So 10 power 18 minus 10 power 15, just to take 10 power 15 common, 10 power 15 I am taking common, now it became 10 power 3 minus 1. So 10 power 3 minus 1 is approximately 10 power 3, 999, close to 1000. For easy purpose I am taking it as 1000. So total 10 power 18 per centimeter cube. And this net doping Na minus Nd is much greater than Ni value. Much greater than Ni value. So now I am going to the regular equations. So the net, okay, now whole concentration P naught is, that means Pp is net doping Na minus Nd, that is approximately, okay, this is approximate value. So its value is 10 power 18 per centimeter cube. 18 per centimeter cube. And N naught is nothing but a Np, which is Ni square by net doping P naught, that is 1.5 into 10 power 10 into Ni square we have, so 1.5 into 10 power 10 by Pp, that is P naught, it is 10 power 18. So now it is 2.25 into 10 power 20 by 10 power 18, it is 10 square per centimeter cube. This is the electron concentration, 225 per centimeter cube. Okay, that is electron concentration. Okay, now I am moving to next problem. So this is not right time to solve this problem because energy gap they given. So later, after derivation of all the equations for energy gap and everything, we go to this next one. See, an n-type silicon containing 10 power 15 phosphorus atoms. So phosphorus means it is Nd. So Nd is 10 power 15 per centimeter cube. Fine. Is doped additionally with 10 power 17 boron atoms. Na is 10 power 17 because boron is Na. This is similar to previous problem, sir. Nothing is different. And Ni they given. Ni 10 power 10 per centimeter cube. Okay, they want the electron concentration. Same thing, sir. Na is greater. So net doping is Na minus Nd. Compared to this, it is 100 times more. You can take approximate. This value is 10 power 17 you get. 99 into 10 power 15 you get. So you can take it 10 power 17. Now whole concentration is approximately 10 power 17. Similar to previous problems, sir. Nothing is different in this. And electron concentration is Ni square by Nd. So 10 power 10 into 10 power 10 by 10 power 17. So this is 10 power 3 per centimeter. So this is the electron concentration. Okay, next one. See, silicon atoms at a concentration of 10 power 10 per centimeter cube. Now the silicon concentration is 10 power 10 per centimeter cube they given. are added to gallium arsenide. Are added to gallium arsenide. See this problem is a little bit different compared to the regular problems what we have. Previous problems we added some impurity to silicon. So silicon is the basic semiconductor. We added impurity to that. But now gallium arsenide is the basic semiconductor. Gallium arsenide is the basic semiconductor. For this you are adding silicon is the impurity. Silicon is the impurity. So that is the point. Okay. Now after adding that, silicon atoms are fully ionized. That means all silicon atoms replace the impurity atoms. So replace the gallium arsenide atoms. And 5% replace gallium atoms and 95% replace arsenide atoms. 95% replace arsenide atoms. Take temperature at 300 Kelvin. Calculate electron concentration per centimeter cube. See, here we are using gallium arsenide is the semiconductor. First of all, for this you are adding silicon to this. Okay. Silicon you are adding to gallium arsenide. If you observed one thing, they mentioned 5% of gallium atoms are replaced by silicon and 95% of arsenide atoms are replaced by silicon. Now with respect to gallium, silicon impurity acting as donor or acceptor. First you should know. And after that, similar way with respect to arsenide, silicon is acceptor or donor. See, silicon is having 4 valence electrons, we know that. For gallium is having 3, 4 plus 3, 7. So it is 8 minus 1. So 1 hole it provides. That means it is Na. And automatically it is having 5 valence electrons. 4 plus 5, 9, 8 plus 1, 1 excess electron. That means it is Nd. So with respect to gallium, silicon acts as a acceptor impurity, and with respect to arsenide, silicon acts as a donor impurity. So now in this semiconductor, for this semiconductor of gallium arsenide, silicon acting as Na as well as Nd. Na as well as Nd. Both donor and acceptor. It behaves like. Okay. Now Na value is, they given Na value 5% of silicon. So 5% of silicon concentration. So 5% means 5 by 100 into silicon is 10 power 10 per centimeter cube. So that is 0.05 into 10 power 8. Sorry, 10 power 10 per centimeter cube. That is the Na calculation, Na value. Similarly, I am going to Nd value because Nd is 95%. Similarly, Nd is 95% of silicon. So 95, 0.95 into 10, silicon is 10 power 10. 10 power 10 per centimeter. So far we know Na and Nd. So that too we observed Nd is greater than Na. Therefore Nd is greater than Na. So once Nd is greater, now it behaves like n-type semiconductor. N-type semiconductor. Now the electron concentration I want to get, and one more. Okay, first I am taking the net doping. Therefore net doping is Nd minus Na. So that is 0.95 into 10 power 10 minus 0.05 into 10 power 10. So its value is 0.9 into 10 power 10 per centimeter cube. This is net doping. You need to compare this net doping with Ni. Now the here intrinsic semiconductor is gallium arsenide. Now you need to get the Ni value of that. They given Ni value of gallium arsenide is 1.8 into 10 power 6. 1.8 into 10 power 6. Therefore, given Ni is 1.8 into 10 power 6 per centimeter cube. Now it is 10 power 10 of the order of 10 power 10. Now it is of the order of 10 power 6. Okay, so compared to this, it is 1000 times more. Sorry, 10,000 times more. 10 power 4 times. So we can neglect that. Therefore, Nd minus Na is much greater than Ni. Therefore, I am writing electron concentration is under steady state, or Nn is net doping, Nd minus Na, simple. That is 0.9 into 10 power 10 or 9 into 10 power 9 per centimeter cube. That is the electron concentration. And hole concentration is Pn, which is Ni square by N naught. Ni square is 1.8 into 10 power 6 into 1.8 into 10 power 6 by N naught, 9 into 10 power 9. Now it is 9 in this 0.2 times 9, it is 1000, 10 power 3. Okay, now it is 0.36 into 10 power 3 per centimeter cube. That is the whole concentration. Okay, so electron concentration is 9 into 10 power 9. Now in the problem, they want calculate the electron concentration. Just to calculate electron concentration. So electron concentration is 9 into 10 power 9. Whole concentration is 360. Okay, so 9 into 10 power 9. Okay, sir. Just a minute. Yeah. So that is the answer. So like that you can solve the problems. Okay, just concentrate a little bit more on problems. And now next session we go to the remaining part. So I'm thanking one and all for spending your valuable time with me. Don't forget to use my code during subscription VROUT10. Okay, and click on this bell symbol for getting the notifications, and join our Telegram group to get the latest updates on our upcoming videos. And don't forget to subscribe it, and please give your valuable comments on YouTube. Those valuable comments are very useful to us to strengthen ourselves as well as to provide a better quality information to the upcoming students. Okay, thank you very much. Thanks to one and all for spending your valuable time with us. Okay, now once again I'm welcoming you all to Unacademy, India's largest online learning platform. Okay, don't forget, outside there is a pandemic. Please restrict your movement. Okay, and whatever thing is happening at outside, your learning process cannot be stopped. So to continue your learning process, join Unacademy. Okay, thank you.